Hey there, welcome back to the channel. If you're a software developer and you're just starting getting into building IoT devices or hardware or things or embedded devices, whatever you want to call them, there are some fundamentals that you need to understand. Some of these fundamentals seem on the face very simple, but they're not always exactly what you would expect. I'm going to go over a few fundamentals in a few different videos. Today, let's talk about digital outputs. A digital output simply is an output on a microcontroller or a microprocessor that we can set a state, assert a state. Commonly, it's either high or low. High is what's called logical high. It might be 3.3 volts, might be 5 volts. It actually can be even above that. It all depends on what your controller is. Most microcontrollers, though, are either going to be 3.3 or 5 volts. Now that high is in relation to a reference, and the reference is usually called the ground on the device. So we've got a ground pin, and then we have an output that, again, will be either 3.3 or 5. It's important to know what that voltage is on the system that you're working on, but for this, let's just assume we're doing 5 volts, and what I've got here is I'm simulating what is inside a microcontroller. So imagine that we've zoomed way in, and inside this, we have this line here, and this is our output pin. So this is our digital out. So everything that happens on this board is going to be what happens inside the chip itself. Now, a digital output is really, in essence, something very simple. It's just a switch. It's probably implemented as a transistor or a series of transistors, some circuitry, but really the logical representation is just a switch. So if we want to set it to output high, all we do is we connect this output to positive voltage. So this is our logic voltage. On this, I have a power supply, just a bench power supply hooked up, giving us 5 volts. So between here and here is 5 volts. This would be ground. This would be our logical voltage. So all we've done is we've connected this, and so this connects down this row here, or I guess this column. What we've done is we've connected this pin to logical high. So if we put this here, and we'll connect to our ground, and we'll use this white as our output. So this would be the output pin, and this is the ground from the computer. And if we check, we have 5 volts of output. If we set the output to low, really what happens is that switch then connects this output pin to the ground. And if we use the meter, we would see from here to ground, you can see just looking at it, that that is going to be 0 volts. So it is an output low. Now that we've kind of looked at how this works, remember, it's either going to be output low, connected to ground, or output high, connected to logic voltage. It will be one of the two. An output is never in an indeterminate state, so not connected here. This we will see on an input, and we will talk about that in another video. But today, let's just focus on the output, because this actually has some interesting effects that are important to understand. Let's assume this is our microcontroller, and we're going to drive something like this, an LED. So there are 2 different ways that we could drive this LED. A real common one is when you turn something high, logic high or on, it will turn this on. So what we would do is we would wire our circuit to the ground of the microcontroller, and then our output to our LED. And when we turn the switch high, so let's move this over so we can see. So when we go output high, it turns it on. That is what most people would expect and most people look at, right? So The voltage is coming out of our pin, going through our LED into ground. So this is powering it on the high side. The other way of wiring this is to have the LED come on when you output low to the digital output. And this one is a little bit counterintuitive. So if we wire one side of the LED just directly to, say, the positive voltage rail on your computer or your microcontroller, and then we hook the other side to our digital output. Now, if we connect this to ground, so setting the digital output to low, it also turns on. Now, it's an output of low, but what's happening is voltage is coming off the voltage rail through the LED, and it's coming into the output pin. So we're setting the output to low, but current is flowing into our microcontroller. That's what I mean when I say this is counterintuitive. So we're really asserting a state on the line. It's called a digital output, but we're really asserting a state. We're either asserting that it is at voltage or it is low. There are a couple more points that are very important on this. In this setup, current is flowing into our microcontroller, and so our microcontroller is said to be sinking current. So it is sinking a certain amount, and at this point, it's sinking about 120 milliamps, which is actually quite a lot. You would, generally speaking, not want to just connect up like this. We'll talk about that here in just a minute. The other configuration we had, where we have this wired to low, this hooked up to our digital output, and then when we switch it to on, this turns on. So now current is coming from the microcontroller's output pin. This is called sourcing. So a digital output can either source or sink power. It's important to understand how much power we're sourcing or we're sinking in here, and to look at the data sheet on your microcontroller, because they will have a certain amount of current that they can source or sink. If you exceed the maximums for source and sink, and they're usually different, they will usually have a different value that they can source or sink. If you exceed that, you can cause the microcontroller, either the gates that are controlling this output or the entire microcontroller itself, to burn up. It will draw too much current. Current equals heat, and it will basically let smoke out of your microcontroller. Just as we've been running here, this LED is actually kind of turning orange right now, and it's because I'm running 130 milliamps through this LED directly, and that is overcurrenting it, and it's actually damaging this LED. If I leave it here for actually much longer, it's probably going to go out because it's fading fairly quickly. What you would want to do is you'd want to put a resistor in here. So here I have a 20 ohm resistor. If I put it between this leg and ground, and then connect to the ground, it still runs, illuminates the LED, and it looks like it is drawing about 80 milliamps instead of the 160 or whatever it was before. And that is an important lesson here, right? So this LED itself has some resistance, but if we remove this and this, and I'm going to turn the switch off real quick so we're not connected at all. If we have this and that output is connected directly to ground, if I set this high, so I set the output to a logical on, it connects this digital output directly to ground, and that Even if we had, say, well, let's assume that this is 5 volts and we had 1 ohm of resistance. You wouldn't even have that, but let's assume that we have as much as an ohm of resistance. You're going to be drawing 5 amps through this output. It's going to be 5 amps for an extremely short period of time when that thing burns up. You could have the exact same thing, so that would be sourcing a lot of current. We could have the analog scenario where we have this connected, say, to power, right? And if we set this low, so connect ground up to this, what we're going to do is we're going to sink that much current. Again, it's a bunch of current's going to flow. It's going to go into this digital output. Again, that's why these things are a little bit counterintuitive. When you have this set as a digital output low, current flows into the pin. So it's going to sink high current, and burn up your microcontroller. So it's very important when you're wiring these up to make sure that your digital outputs aren't run directly to power or to ground, because as soon as you connect them, and by connect, I mean assert either high or low, you can create a short that will destroy your microcontroller. Some micros do have internal componentry that will limit the amount of current that will either be sourced or sunk through this, but you should never count on that. Sometimes that can fail. It can also cause damage to that circuitry. You should always make sure your external circuit has resistance in it to prevent this type of a scenario from happening. And that's all I've got for today. Hopefully you found it at least somewhat interesting. I will continue this series and produce a couple of more videos on the fundamentals that software developers need to understand when building IoT solutions. Thanks for watching.